So this journal club was sort of born out of Emma, Adrian, Johannes, and I wanting our groups to be closer than seeing each other maybe at a conference once a year. And that was even before the pandemic. And then, of course, the pandemic happened and it all kind of came together very conveniently. And we've done this for about a year, that we had a journal club just among the 4 groups. And we thought this year we formalize it a little more and open it up to other groups as well. And then I also became in a very fortunate situation that I got to teach biomechanics to undergraduate and graduate students here at UT. And I thought integrating the journal club into the class would be a really neat way for my students to see what the real world looks like and what biomechanics research looks like in a sort of very tangible way. And so I integrated that into my course. So a lot of my students are actually here today, especially given that Texas is kind of in a disaster state right now, where a lot of people don't have power, internet, or heat, or all of the above. So I'm really proud of them for being here. And so Mehmet is a perfect speaker as being the opener for our journal club. Because as I told my students, not only does he do amazing research, he's also a really amazing person. So that's ideal when you find a speaker like that. And so I just wanted to introduce Mehmet real quick. Mehmet did a lot of his undergraduate and graduate research at UIUC, and then he came for a postdoc to Stanford, for which we are really grateful because that's how we got to meet him. Primarily through Johannes. I'm not sure he's here right now, but since then, Mehmet has been a professor at Stevens Institute of Technology. And his particular brand of research is really neat in that he combines biomechanics with non-invasive imaging, and specifically MRI imaging of the brain. And I think it's a really nice way to open up this journal club, because I think it tells a lot of students that something that they didn't know, which is that biomechanics plays a critical role in the brain. And that's really a discovery that we've made only fairly recently. And so Mehmet combines non-invasive images and non-invasive imaging data with biomechanical analyses to learn more about a number of really devastating diseases that are currently poorly understood. Mehmet is collecting awards and accolades left and right. He's received several NSF grants, including a really prestigious Leap High award. He's gotten 2 R21s from the NIH, and he's, I think, a top 40 researcher in the world on several lists. So without further ado, Mehmet is a great speaker, and so I'm really looking forward to him presenting this talk. Thank you, Mehmet, for being here.
Thank you very much to you and everyone who invited me for this talk, and thank you for your extremely kind and generous words. I mean, if you record this portion, I might include that portion in my tenure package, perhaps. I think that would be a good idea. All right. So without further ado, I guess I'll just briefly introduce the seminar topic today. So this is a collaborative effort between my institution, Stevens, Mount Sinai Hospital in Manhattan, UCLA, and University of Auckland. So quite diverse group of researchers who contributed to this research. And basically, as Manu a little bit described, kind of our main purpose is to combine non-invasive, motion-sensitive MR imaging techniques to understand brain biomechanics. And one of the things that we were interested in, wanted to look at, actually, so John Martinez here, who was the second author, was an undergraduate researcher in my lab, actually, who came up with this idea of trying to look at cerebrovascular mechanics with our imaging methods. And this is kind of where this idea came from, to study aneurysm dynamics and aneurysm mechanics through our non-invasive imaging techniques. We call that A-flow, but I'll describe the history of that and what that means. So don't worry if you don't understand that at this point. So, all right, so just the introduction of the problem a little bit. So intracranial aneurysms are a significant health problem in the US. They're commonly found near the circle of Willis. They can have kind of different locations, like they can be on ICA or MCA. And it's estimated that 30,000 Americans suffer from ruptured aneurysms yearly. So these aneurysms are basically they're like abnormal bulging of the arteries, as you see here. I mean, they can have different forms that I'm not going to talk about today, but quite basically, and in lay terms, they're the abnormal bulging of the arteries. And I mean, within the US and in the world, a lot of people suffer from this. But one of the problems with these aneurysms is that they can be quite unstable. And what I mean by that is that they can rupture without any kind of warning. there's currently no standard clinical biomarker that can predict that. And if they do rupture, the mortality rate is really, really high. It's estimated somewhere between 50 to 60%, even higher, in according to some estimates, but this is kind of like the most optimistic estimate. All right, so currently, believe it or not, the way that aneurysm stability is assessed is through very simplistic morphological biomarkers. They check size, so both the initial size of the aneurysm, but as well as the growth, within the years. So they also check, the clinicians also check the aspect ratio of the aneurysm, as you see here. So the ratio of the height to the width. And location is another parameter that has been assessed with rupture risk. Another method that is less conventional, but it is gaining steam, is using combining MR imaging techniques such as 4D flow, which is an imaging technique that we use in the study and others use too, to measure the blood flow velocity fields within the brain. 3D, and it's a function of time too. That's why we call it 4D flow, because it gives us 4D data sets. And what researchers sometimes do is they take these data sets and kind of develop computational models of the aneurysm and the flow fields near the aneurysm to predict the mechanical stresses on the aneurysm wall, and to correlate that essentially with the rupture risk. So we call these type of simulations CFD simulations, right? Computational fluid dynamics. The problem with these simulations are that, number one, they are extremely costly in terms of computation costs. They can take days and weeks and months to simulate, but also there's no good kind of platform to validate these simulations. So that's one of the main problems with this method. So what we wanted to look at is, we took our inspiration from actually these CFD simulations. One of the things, a few papers demonstrated that high frequency wall motion on the aneurysm wall was an indicator of aneurysm instability. And one of the primary reasons, obviously, for that is high frequency wall motion also means the strain rate is increasing, right? So that's one of the kind of primary mechanical reasons behind this. But there are a few CFD-based papers that demonstrated that and what I mean by high frequency wall motion, by the way, obviously, like, your blood flow is in sync, right, with your heart rate. So anything above that, right, we can classify as high frequency wall motion. Although these particular papers looked into motion ranges, I think, between 5 to 20 hertz even. But it's been shown to be an indicator of aneurysm instability and contributor. So we wanted to potentially measure this high frequency wall motion. But here's the problem, folks. Unlike brain motion in response to cardiac pulsatility, cerebrovascular motion is actually visible. It's actually on the order of millimeters because of just the amplitude of the blood flow. However, wall motion, and especially high frequency wall motion, because high frequency dynamics get damped more, right, than low frequency dynamics. So the amplitude of high frequency dynamics is much smaller than low frequency dynamics. So you won't be able to measure these kind of minuscule motions with standard imaging techniques. So that's why we wanted to try this method that called amplified MRI, which we had first applied in the human brain. So the pioneers of this method is actually the 2D version of it. The pioneers are our collaborators Itamar and Samantha. So what this method basically does, folks, is it takes a video, in this case, a brain motion video that we acquired through an imaging technique called CineMR, That is the original purpose of this method. And then through a combination of different temporal filtering and spatial filtering approaches, we can actually magnify, amplify this motion to make it visible. And I'm going to show you an example of that in 2D. So on the left, you're going to see an unamplified version of the brain motion response to cardiac beat. And on the right, you're going to see an amplified version of that. So let's just watch that video. Yeah, so as you can see, you can clearly see this piston-like motion of the human brain in the amplified version, thanks to our post-processing algorithm. So essentially, our idea was, can we use this method to amplify aneurysm wall motion as well? So that was the main idea behind this paper. However, there are some technical challenges with this that I'm going to talk about. So here, as you can see, actually, I mean, even by looking at this video, this motion is what we call a steady state motion, because it has that standing wave-like pattern where, you know, the motion goes through an equilibrium point and goes back to this equilibrium point, right? That's what we call kind of like a steady state motion. And because of that, the temporal filtering that we use here is based on just traditional Fourier-based filters that uses bandpass kind of filters. That won't work in the case of aneurysm wall motion. And the primary reason for that is because blood flow does not have this type of behavior. Blood flow is extremely transient. So the type of filters that we use here won't work for amplifying cerebrovascular motion. So that's why, whoops, here we go. That's why we wanted to replace the Fourier-based temporal filtering approach that we use in our amplification algorithm for 2D with what we call dynamic mode decomposition, or in short, DMD. And the main advantage of this thing, so this method, as you can see in the formulation here, can decompose a given signal into different traveling waves. Okay, so that's the main advantage, unlike what Fourier transform-based filters assume. And so the main advantage, yeah, that's the main advantage, right? And it can identify the K rate, it can identify a frequency, and the main advantage is that it does not assume the signal to be A, linear, and B, to be steady state. So it can capture transient and even non-stationary data. If the frequency of the signal is changing over a cycle, that's okay for DMD. It can handle that. So that's why, so by using this technique, we modified our motion amplification pipeline. So as you can see here, so we still do our standard traditional filtering technique, but we replaced the temporal filtering approach with DMD. And we also did another thing. So so on the bottom here, you see the amplification for the cerebrovascular motion. So you see the arteries here, we are amplifying their motion. And on the top, what you see is basically the 2D MRI that we have used previously, right, to amplify the brain motion, as I've shown in the video. So we found a way to co-register these both in time domain and spatial domain. And so this is the results, right? So we can actually study the in-sync motion of the brain motion with the cerebrovascular motion. And why did we do that? Because we did that, although this wasn't our primary purpose, we did that because we wanted to find a way to validate in vivo our cerebrovascular dynamics. And the kind of way that we thought about that was, okay, if we can show that the cerebrovascular motion that we extract correlates with the brain motion, that's as good of a validation as we can have in vivo, right? So that's why we wanted to do this, the co-registration technique. And this video that you see here is actually in 2018. So John, the graduate student who worked in our lab, had submitted this to NSF VZ's award in 2018. It was chosen to be one of the 8 most beautiful visualization awards in the United States. Okay, so we first started with phantom validations. And what we mean by phantom is that these are completely simple computational kind of phantoms where we know a ground truth displacement. So in this case, we try to mimic a cross section of an artery, and we used for the flow field, we use a Warm-Mercy solution for a thin wall shell. And we gave a subvoxel known ground truth displacement to this phantom model. We then amplified that motion and studied the correlation between the first between the amplified displacement and the amplification factor, because if this correlation is not linear, then we have a problem. And it is linear, as you see here, but because amplification introduces noise, in certain cases, further noise and distortion effects, we wanted to determine kind of what is the amplification factor that we can use without introducing further geometric distortions in the data set. Because if this relationship starts getting nonlinear, then we cannot use this technique. We also studied the relationship between amplified displacement and internal pressure, because we know from the formulation that that relationship should be linear. We also actually did a further study of whether the ground truth, normalized ground truth displacement, matches with the amplified displacement fields that we extract. So this is normalized. So this is, in fact, the ground truth is a subvoxel displacement that you cannot actually measure. We know that's why we can place this, but in theory, you cannot measure this. So we are amplifying it, and we are showing that the displacement fields more or less look very similar, and the actual spatial distribution correlations are above 90%. So we are able to show that our improved method, which we call A-flow instead of AMRI, can actually capture the displacement maps of a phantom model that mimics arterial wall motion, right? And then we, as I described, we wanted to validate whether the regional cerebrovascular motion that we obtain correlates with the brain motion that we obtain, because that's as good of an in vivo validation as you can have, right? As I described. And we did this for 5 healthy subjects, and we indeed showed that the regional displacements of the cerebrovascular motion and the blood flow correlate within a reasonable kind of range, right? I mean, you want to see usually correlation values above 50%, and this is indeed what we saw, as high as 80% in some subjects. So, and don't forget that blood flow is not the only contributor of brain motion. So it makes sense that this correlation is not 80-90%, but they are correlated. So, we are happy about that. So we can move forward. Another thing that we wanted to check, obviously, one question that you might ask is, okay, how do you know that your newly proposed method with improved temporal filters will work better than AMRI, right? I mean, and it's a fair question. So what we did is we took a really simple intensity variation signal, as we depict here. This is basically the summation of 2 traveling waves with a temporal frequency and two different spatial frequencies. So if these spatial frequencies are equivalent to each other, you basically get still a single kind of wavelength, spatial wavelength motion. So kind of like what we had with the AMRI. But if these K1 and K2 here, the spatial wavelength, spatial frequencies are different, then you're really getting into what we kind of wanted to study, which is the increased kind of wavelength diversity within the blood flow, cerebrovascular mechanics. So, and as you can see here, we wanted to calculate the SNR with this intensity change profile as a function of changing ratios of ratio of K2 over K1. So as you go down here, you're getting more and more, you're essentially moving away from the traditional brain motion, and you're approaching the cerebrovascular motion-like behavior. And as you can see, A-flow, when K1 and K2 are close to each other, performs real similarity from a signal-to-noise ratio point of view, SNR point of view, with AMRI. But as this gets more and more, this ratio increases, what you see is that A-flow's performance is consistent, whereas AMRI's performance decreases because, again, of the temporal filtering approach. It just doesn't, the assumptions fail, right? The assumption of a steady-state wave fails. All right. So the second phase of the human subject experiments that we have done with A-flow is 2 aneurysm patients. So this is a very valuable data set. This is very hard to get, and I will describe the nature of these data sets. So first of all, the type of imaging that we do 4D flow is not a standard imaging technique that clinical, it's not part of the clinical standard of care, right? For aneurysm patients. So we were lucky enough that we had 2 aneurysm patients with 1 year follow-up. So we have in theory 4 scans, right? 4 different scans. So for two patients, we have 1 year follow-up scans. And we know that through clinical diagnosis of the doctor, we know that one of these aneurysms is stable and one of them is unstable. Okay, so we know that to be the case. We basically wanted to check our initial hypothesis. Okay, now that we have this tool, we have developed and validated this tool that can measure, in theory, the cerebrovascular motion and hence aneurysm wall motion. Can we show that in the stable aneurysm versus the unstable aneurysm, there are significant changes between how the high frequency wall motion changes, which has been shown in previous studies, right, to correlate with aneurysm stability. So granted, this is n is equal to 2, but as I described, this is a very hard data set to get. So this is, we don't have any statistical significance here. This is basically just a proof of concept. You can think about it that way, right? So, so this is, I'm just gonna show you how they look like here from a kind of movie point of view. So when we amplify these videos, and so in circle you see the wall motion of the aneurysm location in the first patient, and oh wow, okay, this is the nightmare scenario. The videos don't work. Okay, I will during the Q&A session. I will try to make these work, okay? But we can essentially, the idea is we can extract this wall motion here. Actually, let me, if you just give me a second, let me just make sure. I think they might work.
Yeah, Mehmet, why don't you take a moment and then maybe people can ask questions. I saw that there were a couple of questions in the chat also.
Absolutely, just give me a second and I will,
yeah,
I want to show these videos, so.
Yeah, totally get it. Also, for those of you that aren't part of my class, sorry, I'm putting some comments in the chat window with things that I think that maybe my students don't know, and I'm referring to my students in my course that I'm teaching. You know, don't feel insulted if you're a senior professor and you feel like I'm explaining temporal to you. But I hope that it helps my students. And please feel free to continue putting questions in the chat. Am I monitoring it? And then also Adrian, Emma, please feel free to also chime in as you see need.
Can you see this?
Yes.
Okay, so I will just show it in another slide. For whatever reason, when I moved these videos, it didn't like it. So, okay, so this is kind of for the same patient. What we have, as you can see, the aneurysm wall motion. This is the main harmonic, so this is around the heart rate. And we can, again, this is amplified. And this is the higher frequencies. Okay, so I just wanted to show you those. So, okay, I can go back to the original presentation now. So in theory, we can get videos like this, right, for both aneurysm patients, and we can also measure these, actually quantify this wall motions for the main harmonics, but as well as the higher frequencies. You can see my screen right now, right? Back to the original presentation. Okay, cool. All right, so when we actually quantify this wall motion in the stable aneurysm, as depicted here, versus the unstable aneurysm, these are both, I think, fusiform type aneurysms where the whole artery kind of will just have a balloon. When we compare, so this is basically, so we have 8 graphs here, and I will go over all of them. So this is the control artery, because we want to make sure that, you know, the control artery's wall motion doesn't change significantly, right? So we took the basilar artery as the control artery in both patients. So we are tracking both in the initial and the follow-up scans how the control artery's wall motion changes, right? And as you see, it doesn't change at all. So the blue curves are the main harmonics and the red curves are the higher frequencies. The wall motion in both subjects don't change significantly. It's very similar when we compare the motion of the control artery. But when we look at the aneurysm, folks, here's what we see. So here in the stable aneurysm, when we compare the main harmonic, the change is almost negligible. It stays constant, almost decreases. The higher frequency wall motion increases, which is consistent because the size of this aneurysm also increases, but very slightly. But the increase is about 20%. Okay, if you look at the maximum displacement of the higher frequency wall motion, it's about 20%. When we look at the unstable aneurysm, however, the increase is quite stellar. When you look at the increase of the higher frequency wall motion, it almost doubles, 76% increase in the higher frequency wall motion of this aneurysm. And as far as I can remember, I have to check this, but I think this aneurysm ended up rupturing even. So, this is a highly unstable aneurysm. And the control arteries, the wall motion didn't change. So this is very obviously promising. Again, n is equal to 2. So, this is kind of like a proof of concept at this stage, but I will talk about our future work a little bit that can hopefully alleviate some of those concerns. So as I said, so just to conclude, we just, in this paper that you've read for your journal club, we have extended our previous AMRI technique to incorporate cerebrovascular motion through incorporating transient filters, temporal filters. And obviously we need a large data set for further validation. I would like to thank my collaborators and my amazing lab members and our funding sources. And if you have any questions, I'm happy to answer. And as I said, I might relay some of the questions to American Javed or in the audience. Thank you so much.
Yeah, thanks, Mehmet. That was super cool.
Oh, thank you.
So I'm going to very innocently ask whether any of my students, being both my students in my lab as well as my students in my class, had any questions for Mehmet. Maybe I'm going to ask on their behalf. So Mehmet, imagine you had taken a biomechanics course as a senior undergraduate student or an early graduate student. How do you think that work would have helped you in this research project?
Oh, it would have helped me a lot. Because biomechanics, I mean, especially as an undergraduate, so I didn't take an undergraduate class, undergraduate biomechanics class. It wasn't a thing. I think this is starting to become kind of a standard in the US now. But sometimes I think we make the mistake of thinking about biomechanics as just solid mechanics with application to bio, but I don't think it's that easy. So really, there are so many confounding factors, and biological systems are very complicated, as you saw here. And you have to be able to be more flexible in your way of thinking if you're doing research in biomechanics. And I think kind of laying the foundations of that in the undergrad would have helped me a lot. In conducting a research like this. I mean, something as simple as creating that computational model that we created. I mean, that requires some biomechanics knowledge and understanding. And again, it's not an ideal form of an arterial wall motion, but again, that flexibility is in thinking is something I think that can be learned in undergrad biomechanics education.
Yeah.
Awesome. Thanks, Mehmet. Luke, I think you had a question,
yeah.
right?
Yeah, thanks, Mehmet. That was a really fantastic talk, and I really appreciate the ability to extract kind of biomechanical data directly from the imaging. As someone that does a lot of modeling that takes days, weeks, et cetera, it's really nice to see you can extract that, quicker. So my question was talking about the deformation of the wall. In those images where you had the amplified MRI data, there was a lot of motion in the brainstem. And yes, when we talk, at least when I hear of aneurysm rupturing, it's the deformation of the tissue to the cardiac cycle. So is there any way to separate brainstem motion from pressure cycling through the cardiac cycle to distinguish if either of those is more important or less important?
So if I understood your question correctly, are you suggesting that can we potentially use brainstem wall motion as a kind of predictor for aneurysm stability? Because the more motion you have, you expect that to basically serve as a higher energy source. Is that the question?
Or can you remove that motion?
Or remove?
Yeah.
That's an excellent question. So I think that's kind of what because that brainstem motion is primarily around the main harmonic. So actually, if you separate these harmonics, you are in effect, I mean, you're not exactly doing that, but you're in effect, obviously that brain motion also, that brainstem motion has also higher frequency components. That's a very interesting question, actually. I've never thought about that. That would require a spatial decomposition, like POD perhaps, to extract out that kind of energy source, which would be the dominant mode, and look at the lower kind of ranked modes in terms of like spatial concentration. I would actually, that's a great idea. I would love to look into that. Yeah, that's a great idea.
Yeah, thanks very much.
Yeah.
Awesome. Thanks, Luke, for that question. Mehmet, my student Rudang had a question for you.
Absolutely.
Hi, Dr. Kurt. That was a great presentation. So my question is kind of follows on from Dr. Timmons' question. So here you've used dynamic mode decomposition, which is like, of course, you break everything into these special eigenmodes and eigenfrequencies and then move forward with it. What sort of threshold do you use while filtering out these modes? Because some of, say, the higher frequencies would, I would assume, stay in the really, really high eigenmodes. So at what point do you sort of put your threshold being like, okay, beyond this, we will not look at what this produces?
That's an excellent question. So that would have been a problem. That's a very well-informed and excellent question. So that would have been a problem if we had really high temporal resolution. Unfortunately, so I think I forgot to mention that. We have only 20 phases. So actually what DMD does is return just a bunch of modes almost in a unique way because of the low temporal resolution. 4D flow is an extremely long scan as it is, and its temporal resolution is really limited. So, but that's an excellent question, like how do you decide, right? So the way we decide, obviously we put, I think, I mean, Javed can confirm this, but we put a 95% threshold on the SVD, like singular value decomposition. So if you are able to retrieve 95% of the original signal, we stop there. That's the number of modes that are required. But because of the low temporal resolution here, that's almost equivalent to all the modes. You know what I mean? Because you have only 10 modes that you can extract anyway, right? And then what we do actually, if you want to know a little bit more about the technical details there, we extract, so we don't extract a single mode for higher frequencies. We sum all the higher frequency modes that we find up. So the main harmonics is a single frequency, single mode, but the higher frequencies are basically a summation of all the higher frequency modes that DMD finds. Does that answer your question?
Yes, it does. Thank you so much.
Okay. Yeah, you're welcome.
Well, thank you, Rudang. Thank you, Mehmet. Mehmet, there was one question about data availability. Are your MRI data openly available?
They're not, unfortunately, right now. I mean, as you can imagine, there's a lot of it's complicated with this type of data sets, and we're still processing these, but we would love to make it available in the future. So to be honest, I didn't, so this would be a question that I should relate to my clinical collaborator, because I didn't personally collect these aneurysm data sets. So, but I can, if you can contact me, I can look into that question, but probably it won't be available immediately, but we would love to make it available.
I'm going to provide your email address in the chat. Is that okay?
Yeah, absolutely. Yes, we might be able to do a data sharing agreement. Absolutely, Sanjay.
Thanks.
Yeah.
Adrian,
I have a question that sort of follows up from the previous two questions, which is related to estimating the formation and not just motion. So how difficult do you think it would be to extend this to get some form of strain map? And do you think it would be useful at all? Or do you think just having the motion is enough to assess, for example, the stability of the aneurysm?
That's an excellent question. So as you know, Adrian, as the strain maps will just, the reason why we didn't use strain maps actually here is because that's an extra differentiation, right? So like it's going to even introduce more noise. So that's why we didn't use that here. In theory, we can already do that. But my so Emeric and Javed are right now trying to work on developing image registration methods that are far more robust than what we use. Actually, here what we used wasn't even the best. So we used an open source algorithm called Nifterec, right? Javed, could you confirm that? I think we use Nifterec here, right?
Yeah, for this dataset we use Nifterec.
Exactly. So now we actually we are using a more improved image registration method called Demons algorithm, but we are trying to improve that right now. That's part of our research, and if we can improve it up to a point where we are happy with the SNR, we can actually extract strain maps too. I mean, did we ever look into strain maps here, Javed? Could you remind me?
No, not for this data, because as you said, NiftyReg still needed to be improved.
Yeah.
But with demons, we can potentially also dive into like the strain maps, because I mean, it is very important to check the strain maps here.
Another reason why we didn't look at strain maps was because we were primarily tracking motion in 2D, which was going to give an incomplete picture of the deformation field. Right now that we have that capability in 3D, so yeah, we will definitely look into that. Yeah.
Cool. Thank you.
Yeah.
Awesome. Are there any more questions?
Hi, Professor Kurt. Thank you for the presentation. I had a question about whether you need any, like, if it has to be like a specific Tesla MRI image to actually amplify it, or can it be from any MRI?
That's an excellent question. So MRI typically has currently three common, I mean, just for the audience, three common magnetic strength fields, right? 1.5 Tesla, 3 Tesla, and 7 Tesla. 7 Tesla recently got approved by FDA for clinical purposes. So 3T is the most common. So obviously, for the audience, as the magnetic strength increases, so does your SNR. So you can, in theory, for a lot of the imaging sequences, not for some, but for a lot of the imaging sequences, you can get better, higher resolution with less noise. For brain arsenal, typically people use 3T because 1.5T just does not cut it. So these are all 3T, and I think, I mean, especially for the noise levels that we're interested in, 3T would be the absolute minimum. However, don't think that 7T will be advantageous immediately, because 7T has other problems such as with TE and decreased motion sensitivity. So there's a trade-off between decreased motion sensitivity at 7T and increased spatial resolution. We are working on extending some of these methods at 7T, but it's not a black and white situation. There's a trade-off. So currently we're using 3T, but we would love to move to 7T.
Thank you.
Yeah.
Awesome. Any more questions? I think unless there's any last minute questions, we're going to conclude our very first open journal club in biomechanics called A Closer Look. Very grateful to Mehmet for donating his time.
Thank you for the invitation.
For everybody to be here. If you have any questions for Mehmet, the email address is actually in the chat, and I'm sure you'll find it online. He's not hiding. We'll have the next talk actually on March 2nd. Luke, who's actually here right now, will give a talk to us as well. I'll post, on Twitter and Canvas and wherever I can about all the information. And please sign up for the listserv if you haven't yet. Emma will post the link for the listserv in the chat in just a second. I didn't warn her, so
yeah. Wait, this is a lot of pressure. Hold on.
But anyway, so please sign up and you'll get regular emails, but only one per journal club. We committed to that, so you don't get spammed by us. Anyways, thank you for being here. Thank you, Mehmet, again. Thank you to Adrian and all of our students that joined here today.
Thanks, everyone. Stay safe. Talk to you soon.
See you, Mehmet.
See you. Bye-bye.
Yeah.
I think you were a bit slow, Emma.